straight on to Tim Ebeling from Henning, who's going to talk to us about why a rope suspension means.
Thank you. Ladies and gentlemen, thank you for making it possible that I can talk here. Today I want to talk about wear in suspension means. That is an issue which is existing for 20 years now, I would say, in our industry, which becomes worse, in my opinion. But there are already tools and solutions to detect such wear, to detect the problems, and I would like to show today how it is possible to see from measurements what is happening with the suspension means. First of all, I would like to talk about the things which are causing wear in suspension means. So there are some topics. Rope safety, you all know that, how it is, how much load you have in the single ropes. It is the D-to-D ratio, the ratio between traction sheath and rope diameter, the number of redirections, the construction of the ropes, but all these points are external factors. They are given as soon as the elevator is installed. So during service, during maintenance, you cannot take care about that. Let's call them adjusting screws you have as soon as the elevator is installed are the installation of the ropes, keep care about twisted ropes, things like that, rope servicing, lubrication, and the tensioning within the rope set. And this last point is really interesting and influences the rope wear for a huge portion. There's a tiny formula from Professor Feirer, which is describing what is, so the N is the number of bending cycles, which is describing what is influencing the rope wear. And you will find things therein like the D-to-D ratio I already mentioned, but also the tensioning within a rope set. And the company Pfeiffer-Draco, which is a rope manufacturer, they wrote some years ago a white paper using this formula from Feirer and showing how much the tensioning within a rope set is influencing the rope lifetime. It was a German paper, so the left column, Zugkraft means, or delta Zugkraft means the deviation between the most and less tensioned ropes. And Lebensdauer is the lifetime, the right column. Feirer, when he wrote this formula, expected that a well-maintained lift has ropes which deviate by roughly 25% of the carried load, and defined that to 100% of rope lifetime. So look what is happening. If you decrease the deviation between the ropes just by 5%, the rope lifetime, according to this formula, is increasing by roughly 11%. Decreasing the deviation by 15% already give almost 40% more rope lifetime. So think about a lift which carries per rope perhaps 100 pounds, and the most tensioned 120 pounds, or 125 pounds to make it easy to calculate. Reducing that by 10 pounds would increase the rope lifetime significantly. How is rope tensioning done today in practice, especially with MRLs, but with all elevators? The manual adjustment of ropes is done during standstill. But rope tensioning is not a matter, or the most interesting point, or the most interesting things for rope tensioning are happening during the travel. So the adjustment during standstill is not really the environment of the ropes are facing. And especially if we look to machine room-less installations, for example, that sketch, you find a lot of installations where you are just able to adjust the ropes above the car, like here. So technician stands on car top. What is he tensioning if he tensions there? he's tensioning, if you have steel wire ropes, he's tensioning the ropes between the fixed point and the traction shift, and nothing else. If these are plastic-coated ropes or belts, he's tensioning just a section to this pulley and nothing else. So tensioning 4 meters of ropes, or 6, and assuming that that will be great for the whole lift does not work. And that is what we see. So what we need are these kinds of technicians or different solutions. That rope tension is really an important thing. It's also become, for example, where in 2013, the code in the US, the A17.1, put this section in that ropes or suspension means need to be tensioned within 10%, plus minus 5%, and that needs to be measured. Tensioning or bad tensioning will cause wear in the first step. In the second step, for sure, it will cause, or it can cause, lack of safety. That is a real measurement, and that is something modern overload controllers, for example, can recognize and send alerts for. That is a measurement from 12 ropes over time. That is a down travel. Elevator stands still, start a down travel, constant travel, decelerates, stand still again. It is a high-rise insulation. That is why the loads are decreasing during the travel. It's a tie-down compensation, and during the some 100-meter run travel, the ropes under the car are going to the counterweight side, so we have less ropes on the car side. Sensors are installed on top of the car, and that's why that is decreasing. We see that at the beginning of the travel, almost all ropes have this a similar tensioning, 24 kilonewton, 2,400 kg per rope, roughly. But there's one rope which really has a huge difference to the other ropes. 16 kilonewton, 1,600 kgs, 3,200 pounds difference to the less tensioned rope. So what is that? That is wasting the rope lifetime for sure. And for such an installation, that costs millions. Having 16 kilonewton difference with an average load of 25 kilonewton means we are roughly wasting 80% of the rope lifetime. But what is happening there? Is it just a bad tensioning? So for sure it's not a machine room-less elevator. The technician probably didn't adjust it at top floor. He probably adjusted at the lowest landing, at the bottom floor, so the ropes are close together. But it makes it very obvious where to adjust this setting. If we look for an up travel after this down travel, elevator stands still, accelerates in down direction, constant travel, decelerate, stand still again. And here it is followed by an up travel, accelerates in up direction, constant travel, decelerating, stand still again. Look what is happening with this rope. During the down travel, it was the most tensioned. And during the up travel, it is the lowest tensioned. It is that rope. So it is impossible to adjust this rope. What is it? That is a really bad, or that is wear which already happened to this elevator. And if we look further, here's the up travel, which was the second in the slide before. Here's another down travel. Look what is happening if it starts a down travel. From 1 second to the other during the acceleration phase in down direction, it makes this huge jump over 2,000 kgs, 4,000 pounds. Becomes the highest tensioned again, and then goes to the lowest once again. So This is a worn-out groove. That is the traction shift. If the one groove is worn out, which is the very right in this sketch, it has a smaller diameter than the others. That means per turn of the traction groove, it gives less distance than the other ropes. What is happening during a down travel? It gives less distance, it is the most tensioned. Everything is carried by this one rope until it slips over the traction shift. The opposite in up direction. In up direction, again, it gives the less distance. The others give more distance per revolution of the traction shift, that is, or the others are carrying the load, and this becomes the lowest tension. So it's very obvious, and for sure that is a really, really worn-out installation, but it is very significant what needs to happen to a rope, or what is happening to a rope if a groove is worn out, and that can be detected by algorithms already. Let's look to this high-rise installation. It is roughly 300-meter travel height, one-to-one suspension, and if this groove is worn out by 1/10 of a millimeter, by calculation, it gives roughly 2 centimeters, 20 millimeters, so almost an inch, distance over the whole travel between the ropes. And if you shorten one rope by 20 millimeters, for sure it is carrying the most. With the hundreds of groove depth, it would give 2 millimeter less distance of the rope. So compare that to a standard low-rise machine room-less elevator. Let's say 20 meters travel height, suspension 2-to-1, shift diameter 240 millimeters, something like that. Nowadays, I think they not even call it shifts anymore if you use bouts. If this elevator travels over its whole distance of 20 meters, it gives 17 millimeters difference in rope or bout length if the groove is worn out by 1/10 of a millimeter. And now look to the drawings of modern elevators. What are the manufacturing tolerances for traction shifts of 240 millimeters? They are still the same we had 20 years ago with traction sheaves. So that means the construction of these elevators is already that way that usually you face big tensioning problems. Just by the design, because the manufacturing tolerance would have need to be much more accurate as it is today. Okay, another example, now not with worn-out grooves, twisted ropes. So look to this video. Wow, so you see printed eye lines at the ropes. Not all manufacturers of ropes do that, but it is a very, very handy tool if they do. So during a travel, you would have seen with this video how this eye line is turning, and depending by the rope manufacturer, I think, for example, the company Brook is telling per 100 meters, just 3 turns or something like that. So ropes are always turning. But if somebody did not take care when installing the ropes, you could see that some ropes are turning more than the others, and that is a sign for twisted ropes. If you have twisted ropes, it is very, you can reproduce it very easily. So the down and up travel always looks the same. It is like a mirror in between. And to give you such an example, that is an elevator with twisted ropes. We have here the standstill. The elevator starts an up travel, constant travel, stops, so decelerates, stands still again, and here we have the down travel. The twisted rope is a red one. And you can clearly recognize this rope by just looking for the rope which is increasing over the travel. in an up direction. So what is happening with the rope in up direction if it is twisted? It is twisting more and more. It becomes shorter the distance to the traction sheave. And as soon as it travels in down direction, it does the opposite, but exactly the opposite. And yeah, you can do 100 of these travels and they will all look the same. So also more or less easy to detect twisted ropes from such a measurement. And that is what modern IoT devices or even overload controllers already do. They continuously look to these measurements. They continuously cover the rope tensionings during the travel, can detect worn out grooves. They can detect the beginning of wearing out. They can detect twisted ropes and things like that. So load or the tensioning of ropes, as I explained in the beginning or showed this formula, is really one of the key elements for the rope lifetime. You have seen 40% increasement of rope lifetime, so it's really a huge factor, especially with high installations. You can save tons of money with that, depending if you are the service provider or the the owner of the lifts. Yeah, that is what I wanted to show you. I thank you very much for your kind attention, for your patience with my German English. And I'm open for questions.
Tim, thank you. That was fascinating. So I had a sideways view, which wasn't that great. Time for one or two questions. Is there any? Can't see any hands. I can see a Len. Do I need?
Just quickly.
Look to your left and behind you. That's it.
Just quickly, in your at the beginning of the presentation, you spoke about rope lubrication.
Yeah.
How much does that figure in terms of preserving rope life and increasing rope life?
So unfortunately, I do not have a number for that. That is more about the rouge and the inner wear of the ropes, and I'm not an expert for that, so sorry.
Okay. Question? Don't see any hands out. Tim, I think that's it. Thank you very much.
Thank you.
That was excellent. Cheers.